Hello everyone. In this lecture, I am going to give a brief introduction to digital logic design course. The digital logic design. If I ask you a question, what's the most important gadget in your life? Of course, many people will unanimously say it's mobile phone. Now, what is there inside a mobile phone? The most important component that is present in a mobile phone is a processor. It is compared to brain of a human being. Now let us look at the hierarchy of the processor. In the next level, we have register transfer. Inside of the register, we have gate level circuit, and in each gate, we have semiconductor devices, the transistors. Let me give a simple analogy. If you assume processor to be like a room, inside the room we have almirahs, which are registers, which are analogous to registers. And in the almirahs, we have pencil boxes with pencils, erasers, etc. Here a gate is like a pencil box and the pencils are like the semiconductor devices, the transistors. In this course, we will be working at gate level circuits whose inputs and outputs are in digital format. These basic digital devices, they are called as gates. The function of gates is to allow or stop the flow of digital information. I will get back to you what is the digital information. In fact, they are modules that represent a function which has interconnected semiconductor devices and circuit elements. The functions can be mathematical operations like addition, subtraction, whatever it is. So all such kind of operations and logical operations can be done with the help of these basic digital devices called as gates. The outline of the lecture is like this. We will look at the examples of digital and analog systems, define what an analog system is, define what a digital system is, and try to understand the differences between the digital and analog systems. And also we will look at the advantages of digital systems over analog systems. Here I am showing some pictures of both digital as well as analog systems. The right side figures are the examples of digital systems. If I ask to choose between telephone and mobile phone, obviously we will choose mobile phone because there are a lot of advantages with the digital systems like mobile phones, etc. Also the same with digital cameras, LEDs, LED TVs, etc. Now let us look at the digital and analog definitions in the perspective of signal. So in the light of signal, we will look at the definition of analog and digital. What is the definition of a signal? A signal is a function that conveys information about a phenomenon. A signal is a function that conveys information about a phenomenon. In electronics and telecommunications, it refers to any time varying voltage, current, or electromagnetic wave that carries information. Now, how do we define analog signal? A signal which is continuous in time. The figure on the right side top shows the example of an analog signal, a voltage signal that is varying continuously with time. It has got infinite values, and another important thing is all real world parameters are analog in nature. That is, for example, wind velocity, temperature of sun in a day, humidity, etc. All of these parameters are analog in nature. Now let us look at the definition of a digital signal. It is basically discontinuous in time. Here I am showing a voltage signal that is having just two values, high value and low value. The magnitude of high value is 5 volts and the magnitude of low value is 0 volts. Now when the world is analog, then why digital systems are so popular? Processing and transmission of digital data is efficient and reliable. For example, if the wind velocity exceeds a particular limit, you may have to close a door automatically. Now the process of comparison can be done relatively easily in digital format. Also, when I am speaking over phone, the analog signal is converted into digital format at the source location, transmitted in digital format, and again converted back into analog format at the destination point. Suppose if you transmit the data in analog format, the signal will get attenuated, that is, signal magnitude goes down, and also the problem of noise will be present. The second advantage is, especially in case of storing music stored in digital format can be stored compactly and can be reproduced with greater accuracy and clarity. Another advantage is the absence of effect of noise. What is noise? Noise is unwanted voltage signal or fluctuations. Digital systems are unaffected by noise. On the other hand, analog signals are affected by noise. These are some of the advantages that you have in going to a digital system. If you take any digital system, for example a gate, it will work with two levels or two states. Now we will look at what these states are. How do we understand the two levels or states in the digital system? In this particular simple circuit, a bulb can have two states, either on state or off state. This is achieved by a switch. If the switch is open, the bulb is turned off. That is, the voltage applied is 0 and the state of bulb in logic language is termed as logic low or false state. A turned off bulb is termed as in logic low or false state. If the switch is closed, voltage is applied across the bulb and the bulb is turned on. This state of the bulb in logic language is termed as logic high or true state. Logic high or true state. Turned off bulb is represented by logic low. Turned on bulb is represented by logic high. Well, these bits or states, they are analogous to alphabets in a language. For example, we have languages like English, Telugu, Hindi, Tamil, etc. Now if you take English language, it has got alphabets A, B, C, so on and so forth till Z. Now from these alphabets, you can make a sentence. For example, how are you? How are you doing during this COVID season? Right. Similarly, computer language has alphabets. They are called bits. The word bit is formed by the contraction of the words binary digit. Binary digit. The bits are 0 and 1. So these are the alphabets for the computer language. You can understand it that way. The alphabets of computer are 0 and 1. It looks like it is easy to learn this language because you have got only 2 alphabets. Now, can you just tell me what does the sequence of bits represent, or how do you read that? It has got so many number of zeros and ones. Now, if I ask you that question, it looks a little bit perplexed. Even I also cannot answer this at the moment, right? But one thing is, they are called as codes. This sequence of bits, they are called as codes. Now let me give a brief introduction about binary number system. It is invented by Gottfried Leibniz. Bi is a Latin word which means 2 in English. This brings us to the first 2 digits, that is 0 and 1. All the other numbers are represented by only 2 digits, that is 0 and 1. For example, in decimal number system, you have got numbers starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. After 9, you have got 1 coming back. 1, then 0, it is 10. Similarly here, when you are counting in binary, you cannot exceed 1. So what is the next number after 1? So let us start counting here. So first is 0, then 1, then it is 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? 1 bit sequence changes here, right? If you count the same thing in decimal, it is 0, 1, 2, 3, 4, 5, 6, 7. Alright, so this is how a binary number system is represented. Now let us understand these numbers at logic gate level with a simple example. There is a logic circuit called as inverter. If you give an input, it gives an inverted output. For example, if you give 0 at the input, you will get 1 at the output. Similarly, if you give a 1 at the input, you will get a 0 at the output. In this course, we will be studying with these circuits, the circuits formed from various gates. So this is inverter gate circuit. Out of curiosity, if you ask a question, what is that causing the inversion? Or what is there inside this logic circuit? There is a CMOS circuit formed with the help of 2 transistors, P-channel MOSFET and N-channel MOSFET. These 2 are the semiconductor devices. This circuit works with 2 voltage values, 0 and 5 volts. 0 and 5 volts input voltages. These voltage magnitudes in digital language, we call them as logic low or logic high. If you give 0 volts here, which is logic low, you will get 5 volts at the output, which is logic high in terms of digital language. If you give 5 volts, which is termed as logic high in digital language, you will get 0 volts at the output of this particular inverter, which is termed as logic low in digital language. Alright, now we will look at an important definition, logic level. What is logic level? The set of voltages that are used to represent a 1, that is logic high, and a 0, a logic low, are called as logic levels. Here you have to see the word plural in voltages. In the previous circuit, I spoke as 0 volts and 5 volts, but it is not single valued numbers, but it is a band, voltages. Here we are calling a group of voltages as logic level. Alright. Now, what is this logic level? The set of voltages that are used to represent a 1 logic high and a 0 logic low are called as logic levels. Let me give a simple example. If you have rupees 4,525 paise, how do you approximate it? You call it 4,500 rupees. You don't call 25 paise, right? When we were kids, we were having this 25 paise and all. Now you don't have those things. Similarly, for the previous circuit which I have shown, a band of input voltages like 0, 0.1 volts, 0.2 volts, etc. all are considered to be 0 only, right? Logic low. Now the band formed by 0 volts, 0.01 volts, 0.02 volts is considered as logic low or 0. The same thing holds good for logic high. Band of voltages like 4.9 volts, 4.91 volts, 4.95 volts, etc. They are also considered as logic high. Any value among these at the input will still be interpreted as logic high by the device. Well, for proper operation of the circuit, the voltages are to be within the acceptable ranges that are defined. We have seen logic levels. Now we will look at the digital waveforms. Waveforms that are changing between high and low, high and low, high and low. Waveforms that are changing between high and low levels or states is called a digital waveform. The first figure is a positive going pulse, a waveform from logic low to logic high. The waveform is going from logic low to logic high. The left side edge is called as the rising edge or leading edge. The rising edge or the leading edge. The right side edge is called as the falling edge or trailing edge. Trailing is something which comes behind. Similarly, for negative going pulse, the waveform is going from logic high to logic low. The left side edge is called as falling edge or leading edge, and the right side edge is called as rising edge or trailing edge. It's going from high, going towards low, then again rising. So fall, then 0, then rise. Lead, 0, and trail. So this is how this positive going pulse and negative going pulse are defined, and they are the ideal pulses. They are the ideal pulses. Then how does a non-ideal pulse look like? This is how it looks like. The practical pulse waveform looks like this. It's havoc. It has overshoots. It has undershoots, it is having ringing or oscillations, there is a droop in the curve. Now let us try to understand few of these things. Overshoot is going beyond the prescribed magnitude, in the rising edge, and undershoot is again going lower than the prescribed amplitude in the falling edge. This non-ideal pulse has certain properties: rise time, fall time, and pulse width. We will look at these definitions. Rise time for a pulse is defined as the time required for the pulse to go from low level to high level, or time required for a pulse to go from 10% to 90% of the amplitude. This is the time. So the time required for the pulse to go from 10% to 90% is defined as rise time. Similarly, fall time. The time required for the pulse to go from high level to low level, or time required for a pulse to go from 90% to 10% of the amplitude. Well, going from low level to high level is not defined, for the reason it is really difficult to get the low level point and high level point. That is the reason why we go from 10% to 9%. There is another important definition, that is pulse width. Pulse width is defined as the time duration between the 50% amplitude points of rising and falling edges. So all the definitions are here. I'll just put them over. Now, what are the reasons for this overshoot and ringing? Now, if you look at the circuit may be having stray inductance or stray capacitance. Stray inductance and stray capacitances in the circuit, in electronic circuit, are the reasons for this overshoot and ringing. Now, what is the reason for droop in the circuit? This is droop. The reason for droop is stray capacitance or resistance in the circuit. Stray capacitance or resistance in the circuit. Now we will look at the characteristics of these waveforms. Well, waveforms of digital systems are composed of series of pulses. When you say a waveform of a digital system, it is composed of series of pulses. And these series of pulses are called as pulse trains. It's like train with a lot of wagons. So pulse trains. These pulse trains are again classified into two types. One is periodic waveform. Of course, the waveform which is shown here, the digital waveform which is shown here, is an example for periodic waveform. This periodic waveform will repeat itself after a fixed time called as time period. There is one more waveform, digital waveform, that is non-periodic in nature. So such waveform does not repeat itself. It consists of pulses with random duration. I will show all the figures. All these digital waveforms which I am showing here, right, they carry information. For example, when I am speaking to you, the analog signal is converted into digital format, and that digital sequence is represented like 1 0 1 0 1 0, something like that. So these digital waveforms, they carry information. Now the top figure is an example for a periodic waveform. Time that you measure from here to here, it is period. So this periodic waveform, also called a square waveform, let us assume that the time period is capital T. In that case, the frequency is 1 by T Hertz. How do you understand frequency? The number of cycles in 1 second. So you have got one cycle. Take for example, it is like turning on and turning off of a switch. So manually, if you were to turn on and turn off, how many times you can do? Maybe 1 or 2 times. So in that case, if you are switching a mechanical electrical switch in home, right, its frequency is 1 hertz or 2 hertz. Similarly, if you take a periodic waveform here, the frequency is given by 1 by t. For example, if t is 1 second, capital T is 1 second, right, the frequency is 1 hertz. Now, let us look at non-periodic waveform. This is how a non-periodic waveform will look like. It has got different time periods. Well, it is really difficult to quantify this. Let us look at one important definition that is called as a duty cycle. So if you take a square waveform or a periodic waveform like this, the pulse width divided by total period is defined as duty cycle. If you multiply with 100, you will get duty cycle in percentage. Now let us solve a simple problem. So here we are having a pulse with a time period of from 0 to 10. Again it repeats after 10, it goes on, right? So the time period capital T of this particular waveform is 10 milliseconds. Unit is milli. Milli is 10 to the power of minus 3, right? So the time period is 10 millisecond for this waveform. Now what is the frequency of this particular waveform? Frequency is 1 by t. It is 1 by 10 into 10 to the power of minus 3. 10 milliseconds. So 10 into 10 to the power of minus 3. It is equal to 100 hertz. The frequency of this particular waveform is 100 hertz. Now what is the duty cycle? Duty cycle is on period by total period. So it is 2 by 10 into 100, which is equal to 20%. Alright, so these are the definitions of period, frequency and duty cycle. Hope you understood this. Now let us, before closing the class, let me give brief examples of analog system with the help of a basic public address system, right? As I said earlier, when I speak, the sound waves that comes from my mouth are mechanical in nature. This microphone, which is having a diaphragm, will convert these mechanical waves into electrical signals. So this is the audio signal. Now the magnitude of this particular audio signal is low. Therefore, what we do is, in order to increase or enhance the signal strength, we send this signal through an amplifier. The amplifier will amplify the signal and you will get the same signal which is higher in amplitude. Now this electrical signal, the amplified electric signal, when it is fed into a speaker, the speaker will convert the electrical signal again back into sound wave, which is having a very large volume. So this basic public address system is a simple example for analog system, right? Now as I said earlier, digital systems have advantages over analog systems. So now let us take a simple example where we convert analog data into digital data. Here the top graph shows the temperature in a day, right? I am taking 24 hours format. The temperature in a day is shown in this particular graph. It is analog in nature. The signal is continuous. So the temperature is in Fahrenheit. So somewhere in the middle of the night, it is around 74. Then at say for example at 9 o'clock it is around 79 degree Fahrenheit, right? So on and so forth. The data is given like this, which is analog format. Now if you were to convert this into digital format, in fact there are millions of points that you can get within this graph. So what we do is we sample it, right? So let me give a simple illustration of sample. For example, if you are going to purchase bulk sweets in a sweet shop, right? The shopkeeper will give a piece of that sweet and he says it is sample, right? Similarly, when you have n number of points within this bar, right, we are taking only 1 point. So for a particular interval, we are representing this number by a point. That is called as sampling. Now this sample data is converted into equivalent digital format. Take for example, I am giving a crude example. Here you have got 74 degree Fahrenheit. Now that 74 is in decimal format. Now if you convert the decimal number into digital format, it is equal to 10101010. Right? It is like you are having a logic high, logic low in a sequence, in a particular sequence. So this is how we convert analog data into digital data. Well, in this particular class, we have seen the differences between analog signal, digital signal, advantages of digital signals and digital processing, right? Also, we have seen the digital waveforms and we have worked a simple example as well. And we have seen a simple example of analog system and how analog data is converted into digital format. All those things we have seen. All right. Thank you.